Yeah. So good afternoon, gentlemen. We are happy to have Giovanni Fantuzzi from the University of Erlangen as a speaker today. So Giovanni got his PhD in 2018 from Imperial College in London, and then he moved to, after some time spent at Imperial College, he moved to Erlangen as a junior professor, and he's an expert in semi-definite programming and applications to, say, material science and applied calculus of variation. So I think this is would be also the talk today. So thank you very much for coming.
Okay, I think we are ready. Yeah, so thank you. Thanks for the invitation. It is a pleasure to be here and have the opportunity to give you this talk. So the title maybe is a little bit cryptic, moments, sum of squares, relaxation from variational problems. And so the point is to prevent some work that I've done in collaboration with a number of people, mainly, let's see, David Rodusky and Jason Brandberger and Alexander Czerniawski, Ian Tabasco and Federico Fuentes. And we will, so my background is aerospace engineering, and I like to do problems in fluid mechanics, but we realized that more generally the problems we were looking at had a variational nature. And so that's going to be the message of the talk, is to develop methods, general methods to attack families of variational problems, perhaps in a new way, perhaps looking at old ideas in a new way. So as I said, this is not working, but let's see. Maybe I need to click here. Very good. So the motivation is problems that come from physics that have a variational nature. So this could be problems in material science, for example, if you want to look at wrinkling of materials, if you have a thin shell of material, you want to predict the wrinkling, or you want to predict microstructures, then it is somehow well known, well accepted that these materials, the form of the microstructure forms, in order to minimize the stored elastic energy inside the material. Now, I'm no expert in that. I have a background in fluid mechanics, and it turns out that there are some optimal cooling problems that also have a variational nature, where you're asked to optimize some rate of heat transport. For example, you have a domain like a disk, and you're adding heat in the middle, and you cool the boundary, and you ask, how should I move fluid inside this domain in order to transport heat as fast as possible from the inside to the boundary? Or maybe you add heat here at the bottom of the domain. What have I done now? Okay, maybe I add heat at the bottom of the domain here, and I want to transport it upwards as much as possible. And of course, you can come up with designs, and you ask, are they optimal, are they not? So there are two questions, I guess. How do you come up with a good design? And how do you show that it is optimal? Right, so these are two fundamental questions. Now, rather than focus on this particular problem, as I said, I would like to consider in this talk a general framework, which is perhaps maybe the simplest possible or the most basic one that you can consider. So we want to optimize the integral of some function f that depends on x, an unknown function, which could be a vector-like function u, and its gradient. So the gradient here is just a matrix, a standard Jacobian matrix. U lives in a Sobolev space, let's say W0, 1p, so p is the exponent of integrability. 0 means that u should vanish on the boundary of the integration domain. And to keep things very simple, let's say, I will make standard coercivity, growth, quasi-convexity assumption that ensure that is all minimized. What I will not assume is that the problem is convex. So this function R, as a function of u, could have multiple stationary points, multiple local minimizers, saddle points, and so on. And we're asking, what is the global minimum here? I want to find really the best solution, right? The only non-standard assumption that I will make is that the integrand f is a polynomial function. And this is because I would like to use tools for polynomial optimization that I will review as part of the talk. The two questions that I would like to address are the following. First of all, how do we find an upper bound on this minimum? And second, how do we find a lower bound? Now, these are difficult questions for different reasons. Finding an upper bound is actually not difficult. It's actually easy because, well, choose your favorite function u and plug it in, right? The minimum value is surely less than the value that you obtain for any particular u. However, because the problem is non-convex, the challenge is to find a good function u. Ideally, you want the minimizer, right? So point of the talk would be to find a general strategy to come up with a good guess for what the global minimizer should be, perhaps approximated in the right way. To find a lower bound instead, so these are the side of the picture, requires a completely different line of attack, because you have to make a statement that basically gives you an a priori estimate for the value of this integral, no matter what you put in. So it has to hold for every single function. So the challenge comes even further. So as I said, I would like to address these questions using tools for polynomial optimization. So the point of the plan of the talk is to review tools for polynomial optimization. I will try to give a general idea without getting too much into the details, although there will be some equations that I have to explain. And then after we have the tools, I will apply them first to the lower bounds and then to the upper bounds. And then depending also on how much time there is. If there are any questions at any point, even from the online audience, do not hesitate to interrupt. It is better than maybe we do 2/3 of the talk and have the message come across and do the whole thing and not understand what is going on. So do put your hand up, and I welcome questions. Okay, so let us start with the first part of the talk, which is about polynomial optimization problem. Let me completely forget about these variational problems, and let me just ask the following function. I give you a polynomial f, and I want to, which depends on some variable c, which is d-dimensional vector, and I want to minimize it whilst keeping the value of a number of other polynomials here, g1 to gs, non-negative. This is a standard problem for nonlinear programming. I have some nice continuous functions, but they are non-convex, and I have some non-convex constraints. So even in such a simple case, finding global minimizers for this problem is hard. And this is hard because of non-convexity. So the idea of the people in polynomial optimization, and here we have Didier, who's perhaps the expert in the room about this, is to try and bypass non-convexity by reformulating the problem as a linear problem, but in infinite dimensional space. So the idea is the following. You can show, it's actually not that difficult, that the minimum value of your polynomial optimization problem, which I denote by f star here, can be calculated by minimizing the expected value of f against probability measures, which are supported on the feasible set of the original problem. So I denote it by k. And the idea is that if you take mu b, the Dirac measure supported at the optimizer, then you get the optimal value. Alternatively, you can say that the minimum value of a function on a set is the largest lower bound lambda on this function on the set. So it's the largest constant lambda such that f minus lambda is non-negative on the set k. And now these two formulations are nice because if you look at the first problem, the measure mu appears linearly in the cost, and the set of probability measures is nice space. And but it is infinite dimensional, right? So in some sense, I've gained linearity, but in some sense, I made my problem harder because I moved the difficulty from the non-convexity of the functions to working with a harder space. And in the second case, I want to optimize a constant, but the difficulty is that I have an inequality that I need to verify for all points in a set, and the set is defined by some polynomial constraints here, which could be difficult to handle. So again, I have a linear problem in lambda, because again, lambda appears linearly here in the cost and linearly here in the constraint. But the difficulty is that I have infinitely many constraints, infinitely many inequalities. And checking whether a polynomial is non-negative turns out to be computationally an intractable problem. There is no algorithm that does it efficiently, except for maybe some specific cases. So what do? Well, it turns out that the idea is very simple. And that while checking non-negativity is difficult, it is much easier to check if a certain polynomial, say sigma here, can be written as a sum of squares of other polynomials. Now, it is a basic fact of mathematics that square quantities are non-negative. So if I tell you that a polynomial is a sum of squares, then it is non-negative for free. You don't have to do anything, right? But the other way around is not true. So there are polynomials that are non-negative, but cannot be written as sums of squares in general. But the advantage of this sum of squares representation is that they are computationally tractable. And the reason is that basically a polynomial sigma here of degree 2 omega is a sum of squares if and only if I can represent it as basically a matrix quadratic form where I have a positive semi-definite matrix here in the middle, and I pre and post multiply by a long vector that lists all of the monomials of my variables up to degree omega. so half of the degree of the polynomial sigma. So basically, checking the sum of squares representation over here boils down to finding a matrix whose eigenvalues are non-negative and that satisfies this condition, which is linear in Q. And it turns out that this is what's called a semi-definite program. It is a convex problem and can be solved computationally using software that you can download freely from the internet. So for all intents and purposes, searching for sum of squares polynomials is a tractable problem. So maybe we could use this idea to solve polynomial inequalities. And that's exactly what we're going to do. So if you remember, we had to check my polynomial f minus lambda is non-negative on the separator. And this decomposition, this representation can be searched for with a computer in a reasonably efficient. So in summary, we want to solve a polynomial optimization problem, which is hard and non-convex, although finite dimensional. And the strategy is to lift it into a linear but infinite dimensional problem, infinite dimensional in the sense that here we have infinitely many inequality constraints. And then we use sum of squares strengthening to replace these hard constraints into a tractable weighted sum of squares representation. The last thing that you need to do to be able to plug this problem into the computer is to prescribe degrees for the sum of squares of polynomials, because the computer can only work with finitely many variables. So you can only optimize finitely many coefficients. You can't take an infinite polynomial with a computer. So what you do is you fix some value omega, and you look for polynomials here, sum of squares, sigma 0, sigma 1, all the way to sigma s, that are of degree up to 2 omega. And so this is a problem that you can solve with a computer, and because you make two restrictions, the first is that you represent non-negative polynomials with sum of squares, and the second one is that you fix the degree of these polynomials, then the value that you obtain from this maximization problem, which is tractable, is a lower bound on the global minimum of the original problem. There is also a dual perspective, where instead of starting with this problem in the inequality form for the largest lower bound, we start with the problem of probability measure. The details here are not important, but the main thing is that if you write down your polynomial explicitly in terms of coefficients and monomials, you see here that you have moments of a measure. And then the idea is to write down an optimization problem where you optimize for values y alpha that are basically proxies for the moments of this measure. Again, the details of these formulations are not very important for the talk. What is important is that we have the following three statements. The first is that I can compute these lower bounds by optimizing over sum of squares polynomials, and these form a non-decreasing sequence. The idea is that if I make the polynomial degree larger and larger, I can only improve the quality of my approximation. The second statement, which is key, is that in fact, this sequence of lower bounds converges to the global minimum if the feasible set is, let me say, compact. There are some technical conditions that are slightly stronger than compactness, but for all intents and purposes, we can ensure them. And if you think of a polynomial optimization problem over a box, then everything works, or inside a ball, then everything also works. And the point is not to go into the technicalities, so let me just say that compactness suffices to have convergence. So I can characterize global minimum value of non-convex problems using these methods. And then the third statement, which again is maybe an oversimplification compared to what is known, but suffices for the purposes of this talk, is suppose that my original polynomial optimization problem has a unique minimizer. So there is a unique global minimum, but maybe other saddle points, local minimizer, and so on. Well, then I can extract it by looking at this dual formulation that uses the moment values, by simply looking at the moment values that I find and taking the limit as the omega, the polynomial degree, goes to infinity. Right? So again, here there is some technicalities and some notation, but the point is that we can do two things. And it is that we can solve problems using these sums of squares polynomials, which are tractable. And if we have polynomial optimization problems under some conditions, which in practice are often satisfied, we can find convergent approximations to the global minimizers, to the global minimal values, and also extract the optimizer. Okay, so we can basically solve these hard non-convex problems to global optimality, provided that we can work with polynomials of high infinity. So that's the first part of the talk. And now I should stop and say, are there any questions? Okay, very good. Again, if there are any, do interrupt. So this is all finite dimensional polynomial optimization, but I started the talk with the variational problems. So what's this got to do with variational problems? And how can we maybe do something similar, if at all, to put lower bounds on global minima of variational problems in this talk? So the idea is simple, but it takes a few steps. So let me try and explain these steps in a little bit of detail. So there's going to be equations, but I will explain what is going on. Now, suppose that I can find some function psi, and that depends on three variables, x, y, and z, and another function h that depends only on x, such that f, which is the integrand of my variational problem, plus phi minus h is non-negative. And this should happen for all x in the integration domain of my variational problem, for all points in Rm, and for all points z in which are matrices of sign n by n. Well then, if I have this inequality, I can substitute y for u, which is the function that I want to optimize over, and z, which is a matrix, I substitute in for the gradient of u, which is the Jacobian matrix, so it has the right size. Well then, no matter what function u I pick, then I have this inequality, right? Good. So of course, if I have an inequality that holds on some domain, I can integrate and the inequality remains true. So far, so good, nothing deep. Now, suppose I also tell you that I choose my function psi such that if I take this integral, then I get 0 no matter what function I plug in, right? Well then, this term over here disappears, right? So I can drop it. And I have this inequality. Now, this is true for every u in my isomorphic space. So in particular, I can take my left-hand side and I can minimize it over u. And so if I do that, I conclude that provided I find the function psi and h that satisfy these two conditions, then I have a lower bound of my global minimum of the variational problem in terms of the integral of h. And that's basically the method. Now, of course, you can ask, does this work, or how good is this bound? Well, you can play the game and say, well, amongst all of the functions that I could choose, it makes sense to choose the one that gives me the largest right-hand side here. So you arrive at this min-max type formulation that says that the global minimum of your variational problem is bounded below by the maximum integral of h over functions that satisfy the conditions, right? So it makes sense to maximize the lower one. Okay, all well and good, but how on earth do I do this, right? So there are three difficulties here. The first one is obviously that this problem seems difficult to solve. And even if you forget about maximizing, maybe finding a point that satisfies the two conditions here is not that easy, right? So I want to explain to you how to do that. And for the first condition, you can already imagine that because it is a pointwise inequality, I will use sums of squares and polynomials in order to enforce that. Before we go there, though, I want to talk about the second one because this seems somehow obscure. How do we enforce that condition? How do we check it for all u in some subvolume space? So let me give you a little bit of detail about that. So the idea is very simple. The formula looks complicated, but the idea is simple, and it is to make a change of variable. So instead of working with the function psi, I work with a vector field phi, which is component phi1, phi2, phi3, all the way to phi n. So it's an n-dimensional object. And I will express psi using this formula here for phi, which looks complicated, but the idea is simple because it is essentially what happens when, if you substitute in u for y and grab u for z, then you end up with a divergence of the vector field if you expand this using the chain rule. So if you expand this divergence with respect to the x variable using the chain rule, you have to differentiate with respect to x. So you get a divergence with respect to x here. And then you have to do the chain rule with respect to u, and that's where this term comes from. And then, of course, if my size of divergence, then I can integrate up and use the divergence theorem. I get the integral over the boundary, but u is equal to 0 on the boundary, and so the two terms cancel out, and then the integral is 0. So by construction, a function psi that has this form integrates to 0 for all functions in the soluble space that I care about and that are 0 on the boundary of the domain. Now, there is a subtlety here, and you can actually let this function phi here depend also on the first derivative of u. Now, if you do the chain rule on the first derivative, you will get a second derivative, which you don't want, but you can be careful and arrange for cancellations. And so this leads to null Lagrangians. That's what people in calculus of variation have studied very well. So I don't claim any originality here. So the point is that we are optimizing these phi's over null Lagrangian functions, which are well known, but the explicit characterization is a little bit complicated. I didn't want to put it on the slide. So after this change of variable, I can rewrite my lower bound problem with the original minimization one, which is minimization of the Sobolev function, and we know that this is bounded below by these lower bounds that I obtain by optimizing non-Lagrangian translations. And I will write this non-Lagrangian expression as d of phi, thinking that it's a divergence of some vector field. And you want to optimize that over H, and it's also this vector field phi. Now, before going any further and showing you how to solve this problem, I want to mention that in between these two, minimization and maximization problem, sits a third one, which is a minimization problem over so-called occupation measure, which was studied by PBA and by Martin also. So they know a lot more about this formulation than me. And if you look at these two, you basically realize that in one case, I'm optimizing a lower bound with some inequality constraint, which was like the lower bound problem for the polynomial optimization case. And then in this formulation here, I'm optimizing over measures. So there is some sort of parallel that you can draw between these. And if you see it this way, you can view a chain of steps that you are doing. The first step is you relax. So you take your Sobolev space, functions u, and you enlarge the optimization from Sobolev function to something called occupation measures, which is a bigger set. And then you apply duality theory and you derive the problem of a translation by null Lagrangians. So normally there's weak duality, so the chain is inequality. But it turns out that under mild conditions, we can prove that this measure theoretic formulation gives the same value as the null Lagrangian formulation. This is work with Ian Tabasco. I don't want to go into the details of that. In contrast, the first inequality is strict in general. So we would like to characterize this minimum exactly, but in general, this method doesn't do it. We have examples where it fails and where the lower bounds that we obtain by solving this problem are strictly smaller than this. Okay? So in principle, there is a gap, there is a relaxation gap. But there's also equality for certain classes of problems. So if your integram f were jointly convex in U and its gradient, then it is worked by your colleagues here that there is equality. So you can calculate this minimum exactly. There are also some non-convex cases. So we have examples where we can explicitly construct solutions to the bottom problem and show that a solution, the optimal value, is exactly the value of this minimum. So there are also some non-convex cases which are non-trivial in practice, for which the method works very well. So here's one example. Here's a quadratic minimization problem in one dimension. So here u is one-dimensional function. The interval is one-dimensional. And we want to minimize this quadratic function here, the integral of this quadratic function here, between minus pi over 3 and pi over 3 with zero boundary condition. Now, of course, this is a quadratic minimization problem. Note that the integrand is not jointly convex on U and its gradient because I have a minus U squared. So this does not fall within the class of problems for which there is a general theory. But nevertheless, we can write down all the Lagrange equations. It's simple, we can solve them, and we calculate everything explicitly. So this is a test problem. And now the equations are complicated, but the point is that I can write down explicitly what the optimal solutions for my lower bound problems are. And if you plug them in, you realize that the constraint that you want to be satisfied is satisfied. And if you calculate the integral of the function h, it is exactly the same as the minimum value. So the method is sharp. Interestingly, it turns out that this function h is exactly the optimizer of the problem. And the function phi has this form. It is y squared times minus the ratio between the derivative over the optimizer. So there is this general structure. Don't ask me why, but it just turns out to be the case. So we don't completely understand why this is the case. Yes, Didier.
Phi here, is it smooth?
Very good question. So in fact, it is not. So if you look here, there is a denominator. And if you plug in pi over 3, so the boundary, at the boundary of the domain, this x-dependent factor actually blows up. And you see it in this formulation here, because u must vanish at the boundary. So there is a singularity at the boundary of the domain. But that's fine, because if I replace y with u and z with a gradient, then here I get a u squared divided by u. And so the singularity cancels itself if I do the integral. So this singularity at the boundary of the domain is actually allowed in this case.
So here you write phi as a function of z, but there's no z.
There is no z, yes, that is because my general formulation had phi as a function of z. In this case, we take it only as a function only of x and y.
Okay.
And it's a function in this case. It is enough in this case. Yeah.
And so how good are polynomials to approximate this non-smooth phi?
I will get that in a couple of slides.
Okay.
So this is one example for which we know everything. Here's another example, which is depending on which community you're in, either the Modica-Mortola problem or the Kant-Hilliard problem, where we have a double well potential here for u, where you want to drive u to be either -1 to make this term 0, or to +1 to make this term 0. But of course, you can't do it everywhere because at the boundary of the domain, you have to be 0. You can't be plus or minus 1. So there has to be some transition, and the cost of transitioning is measured by this term over here. Now, I don't know what the optimizer exactly is. I don't have a formula, but I can approximate it for numerically. For instance, in a square, it looks like this. You have -1 or maybe +1 everywhere, apart from near the boundary where you have to go to 0. But I know that this optimizer, whatever formula it has, must satisfy another Lagrange equation. And in particular, it has no zeros inside of the domain. It only goes to 0 at the boundary. And I can use this observation again to construct optimal choices for the null Lagrangian psi, which again depends only on x and y in this case. And for x, and for the function h, sorry. In this case, h is not just the optimizer, it's 1 minus the 4th power of the optimizer. It just turns out that that has to be true. But the form of phi is the same as before. It is y squared times, you see, apart from an epsilon, which is the coefficient that appears over there, I still have the gradient of the optimizer divided by the optimizer. And again, there is a singularity on the boundary of the domain, but not on the side. And if you follow through the calculation, which is on the slide, but I'm not asking you to pass, then you realize that you get a sharp lower bound. Okay, what about the general question, the general problem? So what if I can't do the construction by hand? Because maybe I'm not clever enough. Well, maybe the idea is let's ask a computer, right? And so we can ask the computer to construct feasible solutions to this maximization problem, which is the optimal lower bound that I can place, by using polynomial optimization. So I've already assumed here that f is polynomial, and the rest is up to me to choose. So I can make the following assumption. I have a domain omega here that I need to take care of. And I know that I can handle domain defined by polynomials. So let me assume that I have such a, let's call semi-algebraic domain. So basically omega is defined by polynomial constraints. G as before in the first part of the talk. And then because phi and h are up to me to choose, I can choose them to be polynomials of a fixed degree. And then I can try to optimize them. And that is exactly what you do. You restrict the optimization to polynomials. And instead of now having the inequality, because I'm working with polynomials, I can use this weighted sums of squares representation, which are computationally tractable. Now, if you remember earlier, I said that as the degree increases, these sum of squares conditions converge if you're working in a compact set. Now, I'm not working in a compact set because two of my variables, the y and the z components, live on a full space. Only the x lives in a compact set. However, in some cases, we can still prove convergence, and I will mention this. So that's the start. We can take this problem and put it into the computer. So let me revisit the first example, which is the one where Didier had the question, where we have this problem with the singularities. We know what the optimal h and the optimal phi are, but let's pretend that we don't, and let me optimize a polynomial h of degree omega with tunable coefficients, h0, h1, h2, all the way to h omega. And then for phi, let me cheat a little bit and take a function which is y squared times an unknown polynomial of x. And so if you do this, and you compute the optimal lower bound on the global minimum of the original problem that you find, you get this picture over here, where you see on the horizontal axis the degree of the polynomial that goes all the way up to 100. The dots are the lower bounds, and the dashed line is the global minimum. And you see that slowly but surely, we're actually approaching that value. And this is one problem where, despite the loss of compactness, we can prove that eventually, if you let omega go to infinity, you will converge arbitrarily. You can approximate f star with arbitrary error. And you see that this gap between the lower bounds and the optimal value is somehow decreasing very slowly, perhaps logarithmically, I don't know what it will say. But it is going to zero. The slow convergence is exactly what Didier was hinting at earlier in his question, and is due to the fact that these polynomials are somehow trying to approximate my optimal choices. And while the choice for h is nice, the coefficient here in phi has a singularity. And so I'm trying to approximate a singular function with polynomials. I'm not going to do a very good job. If instead of using polynomials, you use rational functions, so you build in the singularity, then taking a polynomial degree for the numerator of about 4 or 5 already gives you 4 digits of precision. So it works really well.
And there is the coincidence that it's h that arises in the denominator of phi.
In this particular problem, yes, because in the previous one, is not h. It is the optimizer of the original problem. So the fact that you have singularities, it somehow seems to be generic, but we don't really understand exactly what's going on. So here's the other example, this Candeliard or modica mortola problem. Again, I can optimize polynomials, and instead of the explicit formula, which I don't know, I optimize the polynomial phi, this time in 2 variables. And these are the results of a square. I can approximate the global minimum, and I get this value of about 0.47. And here you see the lower bounds for increasing polynomial degree, and you see that they are getting better and better and better, right? Now, because computers are good, but I am not, for this problem, I have an explicit construction, but if I modify it, and I change that -1 to a -2, so somehow I break a symmetry of the problem, then I should look for a more complicated expression here, where instead of just having this term that I had before and I could construct by hand, I also have to have some cubic term and some linear term in y. I don't know how to do the analytic construction in this case, but the computer does it very well. And again, you see that the numerical results converge pretty convincingly. So that's the power of using the computational tools. So this is the end of the second part of the talk. I don't know how much time we have left, but the point is that if we want to put lower bounds on global minimum variational problems, we have technology to do that. It uses sums of squares optimization to optimize these non-Lagrangian translations to construct these lower bounds. We know that the method is sharp for convex problems. For some non-convex problems, although a general theory is lacking, we have examples where the method is not sharp also. And computations seem to behave reasonably well at least for certain classes of problems. So I think it is a reasonably interesting tool to compute these lower bounds in practice. So in the last part of the talk, I don't know how much time I have left.
We can go through say to 60, 40.
Okay, yeah, so we definitely have plenty of time. So the last question is, what about upper bounds? Like I talked about lower bounds, what about the other side? And again, I reiterate that the problem is in some sense trivial, because all you need to do is pick your favorite function u and plug it in. The real challenge is finding a good candidate. So the strategy, and I'm hoping that this is visible, it's a little bit small maybe. The strategy is something which is actually reasonably well known. So what you should do is you should take your problem, which is over a sublet space, and you should just discretize. You discretize, maybe you do finite elements on a mesh, you take your domain, let's say a square, you triangulate, and then you represent your u as a piecewise linear function on this mesh, where the function is determined exactly by the value of the nodes of this mesh. And then you obtain a discrete problem, which is a high-dimensional, nonlinear problem, plug it into a computer and see what it says, right? You also know that if you take the size of this mesh to go to 0, then optimal values and optimizers of this discrete problem converge back to the original one. So in principle, we are done. The problem is that the discrete problem is non-convex. So it is hard to find these global optimizers. So how do we know that we've done it, right? And the idea here is to, which again is, I don't claim originality, it's been done by other authors before, is to realize that if you look at the discrete problem, if you remember, f I've assumed is a polynomial function, then what I can do is I can write the integral over the domain as the sum of the integral over each triangle. And then in each triangle, I know that u is linear, which is an affine function, so I can plug it in and I can integrate. And if I integrate, I get some explicit expression of the variables, I'm going to call them C here, that define the function u on the triangle. So essentially, in this case, if you take piecewise linear on a triangle, then these CT are just the three values of u at the corners of the triangle. And each f here is a polynomial, because what I have here is a polynomial composed with a linear function, which gives a polynomial. So what I'm asking here in the discrete problem is to basically minimize a very large scale, but very structured polynomials, right? Which maybe I can hope to do with this sum of squares technique. I will go one little step further and I will rearrange this sum. And instead of summing over elements, I will group elements together into a macro element. So for example, you take all of the gray elements and you sum them together, and the red ones, and the orange ones, the green ones, the blue ones, and so on. And this is just to rewrite this sum as a sum over terms of macro elements. And this is useful for reasons that will become apparent in a second. So even if I do this, I have a highly structured polynomial function here. And it turns out that methods are being developed by colleagues of Didier, and maybe even Didier himself, that use sum of squares polynomials to attack this discrete problem and exploit this structure. And so the point is that I can minimize this sum of small terms using the sum of squares polynomials, fixing some sum of squares polynomial degree of relaxation order of omega by solving a convex problem. And I can recover an optimal solution to that relaxed problem. And that gives me an approximate minimizer for this discrete problem here, which should be in turn a minimizer for the original variational problem, right? And if I'm lucky, I get convergence. Now, it turns out that convergence at this level we already have by finite element theory, but convergence at this level we have only if we have two technical conditions. One is that I choose my macro element to satisfy something called the running intersection property, which I'm happy to discuss separately if you want. But it's a technical condition that we can ensure by choosing the macro elements correctly. And this we know how to do in theory. But the other condition is that I need compactness. And now if you look at this diagram, you realize that it's wrong because here I'm minimizing over a full space, Sobolev space. If I discretize, the minimization here is also over a whole space. And this is a finite dimensional Euclidean space, but I don't have compactness. So how do I solve this problem? And I'm almost ashamed to say that the solution is basically trivial, and it is to add mesh-dependent artificial and infinity bounds. So we take this problem, we discretize it, and then we artificially say, no, forget about the full finite element space. Let's take a box in this Euclidean space. But the size of this box grows as the size of my mesh goes to 0. So the idea is that if you then take this problem and let h, the mesh size, go to 0, your box increases and eventually covers the whole space. And you can still prove convergence as the mesh goes to 0 of optimizers. The idea is that basically, once your box is big enough, you capture the optimizer. That's all it is. And it's such a simple solution, but it works. And of course, there are technical details that you have to take care of, but one can do that. And what we can prove is that if you choose your macro elements correctly, so that this random intersection property is satisfied, and if this artificial box grows as the mesh size goes to 0, and crucially, the original variational problem has a unique global minimizer, which is a more restrictive assumption, then the approximation that I construct using my sums of squares technology, sums of squares technology that exists, we didn't develop it, then converges weakly in the Sobolev space to the global minimizer of the original problem. And what I mean by weak convergence is that if I take any linear functional and I apply it, and I take first omega, so this relaxation order of polynomial probability to go to infinity, and then the mesh size going to 0, then I get the same value as the linear functional on the global minimizer. And here the order of the limits is important, and because basically you do first a discretization step, and then a relaxation. To undo them, you have to undo them in the right order. I don't know how to switch the order of the limits, or if it's even possible, or what we would get in that case. Okay, so I can approximate minimizers weakly, but I want an upper bounds on the value of the variational problem. And under the assumption that I made at the beginning, I have this inequality always, because basically I have an optimizer and some other function. And I know that this function converges weakly to the optimizer, but the integral functional is only weakly lower semi-continuous. So you could lose values in the limit. So I don't actually know a priori that the values that I compute over here converge to the minimum value. So for that, what we could do is, if we make an additional assumption, then we can actually prove convergence. And the assumption is that the integrand f should be separable, so that the z and y dependence is separable, and that the dependence in z is convex. If you allow me these assumptions, then we manage to prove that if you take the double limit of the values that we construct with the computer using sums of squares computation, actually converges to the global minimum of our functional of interest. And the separability assumption here is done for convenience. I think with some additional technicalities, it should be possible to prove it for general integrands that are not necessarily separable, but still convex in the z variable. But we haven't looked at the details, so this is maybe an open problem that someone can tell me if it's doable or not. I suspect that it should be. So how does it work in practice? So here's again this Kant-Hilbert modular functional. I take the formulation where it's 2 well, so you have +1 and a -2 rather than a -1. And this is because one of my assumptions is that the global minimizer of the problem is unique. And if I replace this -2 with a -1, then I have a symmetry and I lose the uniqueness of the optimizer. So I'm somehow cheating a little bit. But nevertheless, if you solve this problem computationally, you find the guess for the optimizer, and it's this. And it has this value of the integral. So this is the global minimum the functional. And I implement the method for the lowest polynomial degree that I can use, which is this omega relaxation order equal to 2, which basically tells me that I'm using sum of squares polynomials of degree 4. And 4 is the lowest that I can use because if you look at this expression as a function of u is of degree 4, because I'm multiplying 2 squares over here. And I take my artificial and infinity bounds to grow as basically proportional to 1 over the mesh size. And if you solve the problem, you get something like this for a mesh size where I basically take a 10 by 10 discretization of my domain, and you already see that the results are very good. And if I refine the mesh, it gets better and better and better and better. And so this basically is an illustration of the theorem, except I'm cheating because of the last points. And these calculations take these macro elements that I mentioned, and I'm taking macro elements exactly equal to the elements. So I'm doing a triangle by triangle decomposition rather than combining these macro elements. And my computation can actually not satisfy this running intersection property that I mentioned that is necessary for convergence. And the reason, so the reason why it works, I don't know, but the reason why I implemented it this way is computational cost. So here you see data for the implementation with and without this technical condition that we can always satisfy in theory, but in practice actually makes things a lot more expensive. So you see here that the plots that I showed you took very little time to compute. This is the column that you should focus on. Whereas if you decide to use bigger macro elements that satisfy this running intersection property, then you go from half a second to 22 seconds. And then you go from about 3 seconds to 15,500 seconds. And I've already done the math, that's about 4.5 hours. So computational cost grows ridiculously fast if you decide to impose this technical condition in practice. In theory, it is mild, but in practice, it really ruins the performance of the method. So a more interesting example, in this case I actually don't know what the optimal solution is a Swift-Toenberg energy. And this is a typical problem that comes out in pattern formation. So it is perhaps the closest example I have to the motivating questions I had at the start of the talk with this microstructure formation. So again, I'm in a 2D rectangle, and I want to minimize the integral of this horrible quantity over here. You will notice that here I have a Laplacian, which it's a second derivative. I haven't talked about that in the previous slides, but everything somehow extends, the method extends to problems with higher order derivatives as well. And the boundary conditions are 0 values on the sides of the rectangle and 0 gradient at the boundary. And what you can do is you can discretize the problem, do gradient descent, so run the gradient flow dynamics for this functional, and you compute many local minimizers. And you can see that this problem is very good mathematically because it has some equal sign. You get a 1,111, nu, 101, 1 equals to 1. So it's a pretty cool problem. But these are in principle or a priori only local minimums. I don't know if any of them is the global one. So you might think, well, maybe this one, so maybe we should keep this in mind. But a priori, I have no reason to believe that that should be the global minimizer. Maybe I missed something, right? I don't know. So I can apply my sum of squares relaxation because I know that they will, if I implement it correctly, approximate the global minimum. And so if I do that, again, for the smallest possible polynomial degree, so I'm not even taking the limits, and again, with macro elements that fail to satisfy the right technical condition, then I get these results that go for a coarse mesh to a fine mesh. So left to right here, you are defining the mesh. And what you see here immediately in the middle is that I get an approximation that looks almost exactly like that equal sign that seemed to be the best local minimizer. And so this already gives me confidence that that particular function is the global minimizer for my problem. I don't have a proof, but I have strong numerical evidence in this method. But of course, if you look at the other machines, you say, but hang on a second, what's going on? And so it turns out that here, if you make the mesh fine, then you get this oscillatory behavior. And this is due to the fact that in my implementation, the artificial box is getting bigger and bigger. And so I'm somehow trying to solve an optimization problem over a bigger set. So it makes sense that it's harder. Again, this is all vague because I also don't have a rigorous explanation for this, but it's intuition. So I have a problem over a bigger box that becomes harder. And I'm holding the sum of squares polynomial degree fixed here. And so my convergence result says that this polynomial degree should increase. And I suspect that this oscillatory behavior is because I don't have a high enough polynomial degree. If I could increase it, which I can't because my computer breaks down if I do, then I probably would get a better answer. On the other side of the picture, you get this donut shape, and the problem is the opposite. My box is too small. And so I've over-constrained my problem, and I can't capture the true nature of the optimizer. And just to convince you that this intuition is roughly correct, I can repeat the calculation, and I can change the size of the box, and I fix the size of the box so that in the middle it remains the same, but for the problems here on the right, the box gets smaller, and for the problems on the left, the box gets bigger. And if I do that, I get these plots, which are much more convincing. So again, I don't have a strict or rigorous explanation for the numerical results, but intuition seems to be enough. And I think this is the last example that I have, and this brings it to the end. So my outline, in some sense, is also my summary. The main message of the talk is that we can use tools for polynomial optimization to get a handle on global minima of variational problems, either through lower bounds, which you can optimize through this non-Lagrangian translation idea, or upper bounds that use a combination of finite element discretizations that are standard, but coupled with the tools for polynomial optimizations, which come from a slightly different community. And in both cases, we have proofs under suitable conditions that the methods work. We also have computational evidence that the methods work for cases where we don't have a proof. And so I think there are interesting questions here to be answered. If you are interested in knowing more, here are some references. You can always email me, and I'm here for the week. So I'm always happy to talk in person. And I think with that, I will conclude. Thanks for listening, and I'm happy to take any questions.